Hey, folks that are online, we're just going to wait a minute or two before we get started, so just hold on and we'll get started soon. All right, well, I think we're starting to get some people to join in. So I think we'll get started. Hello, everyone. Good afternoon. This is Eric Eula. I'm ESIG's Director of System Operations and Electricity Markets. Welcome, everyone, to this ESIG special webinar. For those of you not familiar with ESIG, we are a membership-based nonprofit organization providing objective information, resources, and networking opportunities in support of clean energy and energy systems integration decisions. We do this through workshops, tutorials, webinars such as this, blogs, working group and task force activities, and producing technical resource materials such as reports and fact sheets. For those of you who are members, thank you for your support. It makes possible these webinars and all the other work that we do. Our workshops and monthly webinars are open to everyone, so please feel to register anytime you see those coming through to your inbox or on the ESIG website at www.esig.energy. You can also find us on LinkedIn, YouTube, Facebook, and Twitter. So let me just a few logistical matters before we start the presentation. First off, participant lines will be muted for the duration of the webinar. That's to help avoid unnecessary distractions. For the Q&A, as we've done in most of these webcasts in the past, we will use the Slido platform, as you see there on the bottom of the screen. So you won't be able to ask your questions through the WebEx chat or through audio. Instead, please go to slido.com and enter in ESIG 10 as the code and be able to ask your question there. And you can also upvote questions that you see to help prioritize some of the questions when we get to that Q&A part. Just a quick reminder on those two, please be respectful with your questions and also sharing questions in there rather than any personal statements or opinions. We appreciate that. So we'll plan to save about 10 to 15 minutes for Q&A at the end, and then we'll wrap it up at the top of the hour. We'll send an email out with a link once the video file has been posted. We'll also plan to provide some short responses to questions that we were not able to get to after the webinar. So please don't be afraid to ask your questions through Slido. All right, so the Energy Systems Integration Group focuses on the integration of all technologies, and while we generally focus on the integration of these emerging technologies within the electric power grid, you might tell by the name that we have a strong interest in the integration of technologies across multiple aspects of the energy sector. That is why I am excited about the topic of today, where we'll explore Power-to-X plans from both a European and Danish perspective. So this includes analysis that couples the electricity sector with heat, fuels, and hydrogen for transport and other sectors across Denmark, with a key focus being how the Power-to-X applications can also act as a large balancing resource that can support the stability of the grid, providing needed grid services from the amount of wind and solar that may be needed to produce the immense growth of electricity demand in that scenario. So today we have an excellent speaker to give his perspective and to present from the Danish and European viewpoint. Anders Hansen is a chief engineer at Energinet, the transmission system operator for electric power, gas, and hydrogen in Denmark. So I also want to remind the audience of a recent ESIG task force, the Flexibility Resources Task Force, which is a group of industry participants looking at flexibility resources, particularly at green hydrogen. That task force published a report last year that explored how electrified loads and hydrogen production could be integrated into planning and operational power system models, and what role green hydrogen could play in providing flexibility to a higher renewable system. So I encourage folks to look at those reports, as well as the 2022 Pathways report that Anders and his team produced at Energinet, which will have a couple links throughout his slides today. So short reminder once again to use the Slido at slido.com with the event code ESIG10 to ask your questions. Without further ado, let's go ahead and get started. So I'm going to turn it over to our speaker, Anders, and Anders, share your screen there with the slides, and the mic is yours.
Thank you, Eric, for this nice introduction. Do you hear me and see the slides here also as well?
Yes, we do.
Okay, yeah, and thanks. And as Eric mentioned, I'm from Energinet, the system operator in Denmark, and responsible for the power system and the gas system, also now introduced hydrogen system. And in my presentation here, I will just start with a short international outlook, especially looking at the European perspective, and then more about the scenarios for Denmark and how we work with this planning for a now political agreed build out of a hydrogen, first step of a hydrogen backbone. Just looking out into international, there's of course very much focus about the climate issue globally, and when it comes to European perspective, as you might see here on the graph in left down here, there's ambitions for reduction towards 2050 to be climate neutral, but also really ambitious targets for climate gas reduction for the coming decades. So that's been a very high focus area for a number of years. But a new key issue is really appearing and has been for some years due to the international situation and the tension with Russia. The methane supply and the import of natural gas to Europe is it's really challenged. So we need to reduce the demand for methane in Europe, and that's the forecast you see here in some different scenarios I'll talk a little more about. So that's really two key issues. So it comes back to security supply, it comes back to the climate issue. And three scenarios are developed at European scale: distributed energy and global ambition, and distributed energy with even very high focus on European autonomy on energy. A few more points from these scenarios. So when it comes to the electricity demand, you see here in the right, due to electrification of heat and transport and a lot of industrial activities, the electricity demand is to increase significantly for the years to come. But also you might see here P2X technology, where you use electrolyzers, use electricity to produce hydrogen, and the right fuel is really a focus area for Europe as well. So much more electricity is needed, and this is to be covered very much by offshore wind, onshore wind, and solar. So that's a totally different system we're looking into, and P2X at European scale plays a significant role. So this one shows the hydrogen demand expected in the different scenarios, distributed energy and global ambition. So it's a significant hydrogen demand, and it's to a large extent to be supplied from electricity, really to reduce the demand for methane in Europe, import of methane in Europe. Then there's also a lot of work with discussions on you might say, scenarios for built out of hydrogen backbone in Europe. This one is here from European Hydrogen Backbone Corporation, working with perspectives for hydrogen backbone, and it's a combination of retrofit of methane pipelines and new hydrogen pipelines. So this is very much about the international situation. One more thing to mention when it comes to security supply. For Europe, the offshore wind is quite essential, and especially offshore wind in the North Sea. But you might have periods, even a number of days, where there's very low wind in the whole area and low solar. That's Dunkelflaute. And this graph actually shows some spots during a number of climate years where this are identified. And that plays really a role when we discuss the need for storage capacity, and it's also Eric mentioned. So we need storage capacity if you have these periods. I think there's actually tried to show, maybe it will work, maybe not. Anyway, but this one is showing just one of these Dunkelflaute periods where if you just go timelines and actually go up to more than a week, where it's blue in whole Europe. There's a lot of wind out here, but we don't have wind turbines out here. So it's really a challenge to handle the system in these Dunkelflaute periods with low wind and low solar. I'll skip this and just come back to this one, because that talks into flexibility requirement for the hydrogen system. Because if you want flexibility for the power system, you need to operate the electrolyzers flexible, but then you need storage capacity in the hydrogen system. And this is the hourly change in a year for one of these scenarios. And this is the accumulated. So at winter time, you might use more hydrogen than produce. And then if you start summertime, you have solar and wind at the same time. You might say you charge to refill your hydrogen storage. So that's really part of this system as well to ensure security of supply. If we look into the planning, the work for the Danish energy system, Denmark has some reduction 2030 target for 70% reduction in climate gas compared to 1990. And it's for the whole economy. So it's for the power system, it's actually 100% green power in 2030. So it's for the whole economy. And then 2045 also climate neutrality for the whole economy. And the focus is also, of course, the green transition, but security supply is really top of priority in the work and the planning we do. And of course, it needs to be cost efficient. So it's really optimizing these three parameters to get the most cost efficient climate transition, keeping security supply and do it in a cost efficient way. If we look a little more on the transition in Denmark, there's a lot of the direct electrification, as also mentioned by Eric, with electric vehicles. I think today more than 60% actually of new sale of vehicles are electric. So it's really booming now. Industry also with the heat pumps. And then when it comes to heavy transport, it's actually a mixture of electrifying heavy transport, but also using fuels produced from hydrogen. I'm a little back to this. And heavy industry needs also fuel to make high temperature heat and burning processes. Shipping and aviation as well. Then when we talk about the different, I'm sure most are familiar with this process, but just to take it quite short, take electricity, water in and electrolyzers, and then you produce hydrogen as a primary product, but you also have some excess heat and some oxygen relevant for other processes. Then you can use the hydrogen for heavy transport, for refineries, for steel industry, but also as a peak load capacity. So we do analyze using gas turbines with hydrogen as well as peak load, but it's only a very small part that goes back to the power system from hydrogen. then producing ammonia to be used for ships and bunker fuels and fertilizers, and then combined and from ammonia combined with the nitrogen, but also to use oil, you might say substitutes. You need to combine it with CO2 or biomass to get the carbon and then produce methanol and jet fuel and gasoline. So that's really an essential products, and also chemicals and plastic products. So looking into the Danish transition, this is the forecast we're planning with at Energinet for the power system and the other energy system as well. So we have from this electrification of transport and heat pumps and increase in electricity, but it's not, they're so very efficient actually. It's not that much electricity they need an annual consumption, but it's very large capacities and flexibilities we get. And then there's, as everywhere, data centers really to boom, and then there's P2X. So that's really a significant increase in electricity. So when we think in Denmark, we have the significant increase in wind, and also now starting in solar, we just realize that we haven't seen anything yet, because the capacity, and beware, this is the capacity, not the produced annual energy capacity for solar, offshore wind is just significant to increase. So we need to, or we do analyze how we operate this system in our scenario analysis until 2050. So we have offshore wind, offshore resources in the North Sea, close to Denmark, maybe 3 up to 5 times what we actually need for the full transition of the Danish system. So it's very much producing energy to export to Europe as well. Then when we are talking about the offshore area and also P2X in this, what we really have focused on now is offshore production of electricity feeding into shore, and of course feeding into the electricity system to the grid, but also at the feed-in zones install electrolyzers, so you have the flexibility to switch between using for electrolyzers or feed into the grid to have them, you might say, even more stable supply of electricity here. So that's a key one we're looking much more into. But we also look into having offshore hubs with electrolyzers. So where you have this hubs offshore, there could be electrolyzers, but it's more than 10 years ahead. We're looking into to these kind of projects, but it is an issue. And also when it comes to the turbines, hydrogen turbines are looked at the developers, so that could be as well be a combination of this. Then there comes a little nerdy one, but just take it when we are discussing about the offshore renewables we produce, as just shown here, going in the electricity and potentially offshore hydrogen production. And this was to show some of the processes being aware. There's a hydrogen grid, and then you might use the hydrogen to produce ammonia for fertilizers and ships, and then you might use the hydrogen to refine, but then you need some CO2, some carbon for refining towards oil substitutes. That could be from captured CO2 from the CHP plants. That could be from CO2 from the biogas. When you clean the biogas, you get CO2 as well, and you can crack this towards refinery. And also you could take your natural gas and crack this in electric steam reformer to produce this. So a number of processes actually combined here. And the red one shows actually heat. So there's a lot of excess heat from all this process, which has some nice synergies with CO2, where you can use direct air capture, uses a lot of heat, and that really make it more competitive. So I'll not go more into this, but just saying at this activities on this hub are showing in the next slide, there's a lot of potential combinations here. So this is what we can see in this hubs analyzed in different joints in the system. So we're now in Denmark looking into investigating, planning this hydrogen backbone. So this is the different grid parts analyzed, not all of them to be built. But now we're especially analyzing this towards Germany and the first part here. And that comes into the analysis methodology we use here. So we have the representation of the grid, the power grid, and the representation of the hydrogen grid, and then we do this co-optimization. Yeah, I think one thing essential to mention when it comes to the cost, you might say unit cost per capacity per kilometer, then overhead lines, well, they're quite, you might say, cost efficient, but it's really politically challenging to build out overhead lines. So you, for a number situation, might need to go to cables, which is significantly more expensive, whereas hydrogen pipes are actually quite cost efficient as well. So if you build out this, you do co-optimize by these parameters for the build out infrastructure. And then when it comes to storage cost, we see a lot of batteries to come in Denmark, like everyone does at the system. Large scale batteries are still very good for hourly or maybe into 1 day storage, but when it comes to this seasonal storage, the unit cost for storing hydrogen in cavern is very cost efficient compared to batteries. So this is the fast muscle, you might say, for hours storage, and this is for days, weeks, even seasonal balances when we do this optimization of the system. So when we put this into our least cost system optimization model, where we use bit, other one might use Plexus, but for our part it's bit free we use. We put in this parameters to do the system optimization, and then we give the input of our renewable resources we have out here, the way we can invest in grids, and then put in the demand, how much power consumption is expected, or the willingness to pay for power consumption for methane, for hydrogen demand, and for derived hydrogen fuels. And then in the model, just do the least cost optimization, you might say co-optimization of hydrogen grid and electricity grid. What's the cost efficient way to build it out, and then also expectations for what the market will invest in heat pumps and P2X plants and CO2 captures, and then of course also dispatch run. Yeah, Eric, I think you just interrupt if there's a question related to this on, otherwise I'll just continue here.
Yeah, I don't see any coming up yet, so
okay, I'll just continue. So when we are talking about this least cost system optimization model, I think it's relevant to touch on other models we use for this system analysis. As mentioned, we use the European TNDP and SUI scenarios as an international framework condition. We have our analysis assumption for what's the cost for grid, power grid, and for hydrogen grid and gas grid. That's the technology data costs here. And then in bit 3, we do this co-optimization with the representation of the grid. And for more detailed simulation of a grid, we put it into Power Factory and do some even stability analysis in Power Factory with RMS, but also at PSCAT with EMT simulation. So this is, you might say, the linear process in this optimization. But also when it comes to the flow for the gas and for the hydrogen, we use hydraulic analysis in Simone program. So that's, you might say, integrated these processes, but we're looking into and come back to this more integration of these packages. So just to finalize about our hydrogen grid. So now we actually at the situation to to look further on investment in this first part of this hydrogen grid and learn more on this. This one is actually a 2050 example showing a hydrogen grid, and this is simulated the annual or the hourly variation during 1 year where we use storage in this caverns. And this is a Sankey diagram showing power going to different consumption, but also as you might see a lot of the power actually going to hydrogen. This is an annual Sankey diagram with hydrogen going for the industry and transport and export. And then also, as mentioned, you combine this hydrogen with sources of carbon to produce oil substitutes. So it works together, and it's all about doing the most cost-efficient way. Then when we look into this scenarios, of course, there's in the hour and even in the operation, 50 minutes operation units, looking into much more imbalances due to much more wind and solar. So we of course look into the constraints we do have for this you might say changed system. This is the variation from large solar plants. It's very popular to have large solar plants in Denmark. We don't have so much rooftop at the moment, but that give really significant variations. Then of course the congestion in the grid, and then another constraint to look in is to ensure we have enough stability in the system, so we are losing much inertia as we have so much wind and solar running most times, so there's no operation in many hours for the central power plants delivering traditional inertia. So synthetic inertia from wind, solar, from batteries, and also some of the ancillary services to be delivered from electrolyzers, potentially combined with batteries, is a huge source of, you might say, flexibility. And try to show this in the next one here. So this one is a duration curve, and actually a 35 gigawatt offshore wind in North Sea scenario. So this is the wind and solar, and the yellow one here showing the flexible consumption. I'm not sure if it works with this. Maybe this one. Anyway, this is the flexible consumption. So due to a lot of electrolyzers running, a lot of heat pumps running, a lot of electric vehicles running, there's always a lot of flexible consumption available. Whereas the thermal power production shown here in red is so low compared to all the other, and most of this is some running like waste incineration most times. So it's really wind and solar dominated. And of course, with much more forecast errors in wind and solar, you might say, do we have enough flexible consumption to deliver needed ancillary service? So we do from units from D2 program, the University D2 have some model to forecast to identify the forecast error and day ahead or hour ahead. So this is the forecast error in this scenario. And then if we look at the forecast error and try to compare this with the flexible consumption. So this is at the x-axis, you have the flexible consumption and the forecast error. And then of course you might say, you might have hours where your forecast more, you get more wind than expected. And that's from security supply, you can down regulate this. But then you also have situation with much less wind than expected. But as long as you have flexible consumption to regulate down, you're actually safe. So we have a huge access to flexible consumption by these electrolyzers and heat pumps and all. And then you have some red shown here where you actually have more forecast errors than you have flexible consumption. Then because you need to operate potential thermal power plants to get them ready for running there. And of course, talking into probabilistic analysis, you have to be to be more safe and have a large you might say additional resources. And that talks into so next, I've been talking a lot about planning, but also if you look at the system operation of this integrated power and hydrogen and gas system, we do have this forecast errors we have to look into in our optimization. We have to look into stability. Do this operation point we're looking into deliver stability. We might have to look at the hydrogen system as well. So if we look at the pressure of the hydrogen system, you might not be able to regulate up and down your electrolyzers if you are at a low pressure level. So you have to forecast and ensure you optimize your hydrogen operation, of course your wind and your stability, and of course also all the transmission congestion in the grid, and even looking into now congestion in the distribution grid. So actually really quite advanced optimization we're going to look into if you have this co-optimization of power and gas system. And then we also look a little into how could you use more, and it's very much discussed, use of AI and the more computing power and control theory to optimize this. You might use advanced control field like model predictive control to optimize so many constraints in a system operation when you look into more energy vectors. Talking about using AI or machine learning, I'd also like to mention a little that we do have in our planning studies. Of course, we have a number of scenarios, in this case 1,000 scenarios, and we starting using instead of always simulating, really try to use AI machine learning models to see how is the correlation between all these parameters. So you actually have a trained model, so you can say, well, what happens if one parameter changes? How does that influence other parameters? How does it influence the system economy? So we starting using this, you might say, methodologies in these areas, and that actually leads into a discussion on where could we also use these methodologies. And this one is from the University DTU here, where they present and like to discuss and also hear positions on that. If you have a database with maybe a lot of stability analysis, it could be Power Factory, RMS, or it could be PSCAT and other of the EMT simulations. And you actually on all this identify, are they stable or unstable or maybe uncertain? Then you have all these, you might say, simulations and a trained AI or neural model, and you can use this model to identify or at least screen to see, is this a stable or not a stable situation? And then we're looking much into, could this give us more information about metrics we use in our planning? So if we look into a system where you do this least cost optimization of the system, we don't usually look into stability. We add on stability afterwards. But actually we could in our bid system introduce some metrics used as input for identifying, you might say, metrics showing if it's stable. So it might be your short circuit ratio. But you could also in this model actually make a request to this model, to this trained stability model. So you could somehow combine your analysis for the planning where you also have the constraints of stability and then co-optimize. So you might deliver stability from your battery, or you might choose to have your grid forming assets additional cost, but delivering additional stability. So somehow we think it's very interesting to understand how do we combine AI methodologies with our traditional linear optimization or milk optimization, but it's not something we do, but we really would like to discuss this further also. Also distributed resources response could be a good way to train and learn response and use this and now to integrate planning. So I think by this I will start summing up and maybe hope for some questions. There's definitely very high ambitions for renewable energy with electrification and sector coupling. And what we see is really that co-optimization of power and hydrogen system in both planning and operation is really a key issue. It highly influences our planning of our power system, but we also see it will highly influence our operational systems. So control on the future should plan in for at least an overview of hydrogen system. Then there's, of course, the congestion management and this tight coupling of market physics to have values of both central and distributed resources, and also knowing the dynamics for the different system. That's a new, you might say, issue to work with. And then we, as point 4, really see computing power, AI, and new control methodologies open this opportunity for more market-based integrated energy system. And all this calls really for some more focused R&D and demonstration of prototypes. So by this, I think I'll conclude my presentation here, just saying we really see a lot of issues about co-optimization of electricity, hydrogen, and gas system.
All right. Thanks, Anders. So we do have several questions, and I'll just encourage folks to keep adding those in, and we'll, even if we don't get to them, we do have plenty of time to get to many of the questions here, and if we don't, we can always respond to some of those offline. I hope I'm understanding some of the questions correctly. Maybe you would understand some of them better than me, Anders, but I'll just kind of go through some of these, and some of them are kind of similar, so I might combine a few. Looking at one of these, I think just can you elaborate or share a little bit more details about the kind of the level of dispatchability of the hydrogen facilities, maybe like how fast they can ramp, any kind of additional information or the parameters that are used for, how they are dispatchable, any challenges, with that level of dispatchability?
Yeah, and it's really a good question and a key question, because it's so different for the system depending on how fast they can react, and also will they regulate down in situations with where there's very high prices. So what we learn and see until now is that the first one setting the plants up might already have made the PPA and other agreements and might expect to run more steady, you might say. But we also know from developers, they are building and installing so they can regulate down. And we got in our technology data publicly available, and I can put out after this also in the chat the technology data we use. We can actually, from the electricity side, regulate very fast the electrolyzers. And that comes back to essential about having this hydrogen backbone, because the electrolyzers might have an agreement with a consumer producing ammonia or derived fuels, or maybe export to Germany. And I mean, they can't regulate down unless they have storage capacity. So, but if you have this storage capacity, you can regulate it very fast. Actually, going down to, yeah, it's uncertain where you can take 10% per second, actually discussed on the electricity side. So very fast. Also to say, what we all see that they are combined with batteries. So you might not need this very fast response from the electrolyzer. So what we might see is to take this sharp thing with the batteries, and then you can regulate down within some minutes for the electrolyzers, because you can always have batteries for the first minutes. So combination of batteries and electrolyzer with hydrogen storage gives an eminent flexibility. Batteries for the very fast, electrolyzers within some minutes, and then you have storage capacity electrolyzers, so you can turn them off for weeks without problem. So it really is a huge, you might say, flexibility source if you can operate it. But I'll be happy to share what technology data we use for this.
Great, thanks, Anders. Just maybe adding on to that a little bit, how, you know, kind of talk a little bit more about the if you have the information on it, how much of the physical characteristics of the pipeline system are you modeling in there? In other words, you know, how physical is it within? Is it kind of like the standard, you know, like just a standard transportation? Like how much of those details are you actually representing?
Yeah, what we do in our bit-free modeling, and that's comparable to Plexus, is we model the line pack in the pipeline as an, you might say, actually as an electricity storage. So we have the line pack, and just to say, line pack is the storage of hydrogen you have if you change the pressure, and you have to operate, as I showed, within in a range of your pressure. So if you stay within this range, you can store hydrogen because you change the pressure, but you're still within an acceptable level. So this model simply as an, you might say, electricity storage. But then, so it's simplified in this way. But then we take it into to the model. I think I showed it here. So we take from our market modeling into our Simone, and that's hydraulic model. So we take this to see, is it fairly represented? Because it's very much simplified just to say, well, the line pack acts as a battery, and the large storage as well, where we have this and caverns and salt caverns, actually a hole in the ground where you can put with a pressure. That's also hydraulic. So very short to say, we simplified it in our market modeling, but we represent the storage, and then we put it into Simone to see, is it fairly represented? So you might say it's similar to what we do about the physics in the grid, still simplified in our market modeling, and then much more detailed, simulated in Power Factory and even PSCAD, the EMT. But that also comes back to, that's where we want to be better to connect with maybe machine learning to have it better represented. Yeah, sorry for the long answer. But...
Great, thanks, Anders. So a couple of questions around costs. You know, comparison of costs across, you know, well, hydrogen compared, you know, what is its cost compared to other, you know, types of technologies, long duration storage, other things like that. You know, a question around storage costs. How does storage costs for hydrogen compare to ammonia? And then also around, you know, how important is subsidies in making hydrogen cost effective? So maybe just kind of, you know, capturing some of those questions and sharing your thoughts on, you know, sort of the cost comparisons and in what you're using for your assumptions, but also, you know, how do you see that coming up in practice in the future?
Yeah, and really about the cost and the market cost and need for subsidies. I'll come back to this really. Just to take shortly about the cost for storage, and I know when I showed this graph showing what's if you compare to battery, maybe with $100 per kilowatt hours for this storage. When it's stored in a cavern, that's much cheaper. It's really below, significantly below even $1 per kilowatt hour. So it's much cheaper to store. But of course, that only makes sense if you have it as hydrogen, because the conversion, so it doesn't work at all to convert to hydrogen and then stores hydrogen and convert back to electricity. That's round cycle efficiency is below 40%, maybe only 30%. So that doesn't work. So what I showed this storage cost here was, and you also can find this in. Maybe I'm sharing here. Yeah, I'm sharing. Okay. Yeah, you can find more detail also in technology data for these costs. So basically, it's about if you have to go to hydrogen, you want to do the storage on the hydrogen side, but never go the round cycle as hydrogen back to electricity. So that's this cost storage, and we find more about this. And then the other thing that's really tricky thing is, what is the cost for producing hydrogen compared to fossil reference? So when we look at technology in the long term, and that's beyond 2030, maybe 2035, the green ammonia and the blue ammonia, so that blue that's made fossil, but then you capture the CO2. The green ammonia is competitive, so you might come down to maybe $2 euro-dollar, that's close to the same per kilo of hydrogen. But the production cost now is significantly higher because there's so much R&D. So you might be uncertain to say, but we might have $4 per kilo hydrogen. So they definitely need subsidy in this transition. It seems not we can compete with you might say fossil hydrogen at the moment. So, and we sometimes try and say even long-term cost for production of derived fuels, you might say jet fuel. And I'm not good at gallons, but if you take liters, you can come down to a price on maybe $150 per liter, maybe closer to, still more than $1 per liter for the raw production of this fuel. And that's, as you know, the fossil prices are significantly lower. So it is more expensive. That's the situation as is. But, well, we need to reduce the demand for methane in Europe, definitely. So that's a little about the cost, and feel free to ask more. I'd really like to tell all I know about it, but yeah.
In anything around the subsidies, did you?
Yeah. So I actually just said that production is cost is significantly higher for the coming years. So there might be, we don't do subsidies in Energinet, but there might be definitely a need for subsidies unless the market will pay additional for green hydrogen, and that they might pay more, but not, I mean, double or 3 times prices. So might be another way of doing it could be mandatory blendings in fuels, like for aviation fuel, blending some green fuels in this, and blending green fuels also for transport sector. That's needed because it's more than double price. So that's, but in the long term, looking at the data, it's seems quite obvious that it could be competitive with fossil hydrogen, but it will take some years. Then there was a storage cost about ammonia compared to hydrogen. So ammonia is even cheaper to store than hydrogen. But then, of course, if you need it as a product, as ammonia, it makes sense to store it as ammonia, but not converting back to electricity.
So Anders, kind of another related question that that came up is, so I think Denmark historically experiences a good amount of negative prices, and across Europe, I know there's good amount of those negative prices. Does that show up in the modeling, and is that a big factor into some of the economic build-outs that come up with the modeling, those negative prices or zero prices?
Yeah, in the modeling, we actually not fully able to model negative prices. So it's typical some specific situations where you have production don't regulate down, but as a wind and solar just curtail in the model, we don't have negative prices. I know they appear today. There might be situations, there might be some feed-in regimes and other things that just bring a situation with negative prices. We don't have that much now. 1 year ago there was more, but that's very much due to some rooftop solar with very stiff or fixed regimes, but that's really changed now. Just one comment about negative prices. So in Denmark, I would say all end users are settled by hourly prices. They might have some other agreements, but mostly actually settled hourly prices. So they do respond in negative prices. So you produce more, but also if you have rooftop solar, you regulate that down. That's one thing. But then you said, are there many negative prices? I'd say the new situation, we used to have on the margin the gas turbines as the high prices. But what we see now is actually the price of hydrogen drives a number of hours. You got electrolyzers on marginal consumption, so they set the prices. But we still have maybe thousands or 1,500 hours of zero prices. That could still be situation. Yeah, so but incentives for investment in batteries just captures. It's not really a big. It's an issue, but it incentivizes new consumption also with low prices.
Thanks, Anders. There's a couple questions here, and I don't know if it's you talked a bit about some of the grid services and how hydrogen can meet some of those. There's a couple questions around inertia, and in these scenarios that there's a reduction in the amount of synchronous machines that will be on the system. What's left to provide inertia? Maybe a little off topic from this, but I wonder if you have any comments there.
Yeah, but it's definitely very relevant because as presented, we don't have many hours with central power plants with inertia from synchronous generators running. So it's really a very much, you might say, inverter-based system we're looking into. So grid forming from batteries is coming, I think, globally, but we also look into what kind of services you can get from electrolyzers. So I mean, if you combine it with a battery, they have capability to deliver grid forming, and you can do P&Q setting, deliver voltage support as well for these. And if you have battery, you can do the very fast and grid forming response. And this is, as it is hybrid, we're looking into everything. Many things seems to be hybrid with batteries. So when it comes to solar, hybrid batteries, but also when it comes to electrolyzers, hybrid with batteries. So, and I think a very essential thing to say on grid forming capabilities. So these consumptions are in large central points in the grid. Whereas if you have offshore wind, maybe in distance on 30 miles or even more. Electrical is not that close connected to the central point. So now you have assets in the central points in the grid with your electrolyzers, and especially your batteries combined to electrolyzers. So that gives you good points for delivering grid forming capabilities. But something that started, we're looking into it, what you might say, the hybrid makes it very relevant to deliver grid forming.
Great, thanks. I see a few questions on the AI application. So I'll try to kind of combine those. So one question was asking, how important is the AI and ML to this optimized operation kind of out of the gates, right away, compared to building that up, over time. And then the other question was asking, is AI helping specifically to predict some of those, low inertia type situations in the modeling?
Yeah, I have to say in the modeling, the use of AI is just one, you might say, initial experiments we're just doing now. Definitely the whole modeling was based on linear optimization, but then on top of this we trained a model from a machine learning model on all the results, and to say what do we digest of relations and multi-parameters. But we haven't worked that much with this, but working even the little thing we've been working in, we see high opportunities on this. And especially there might be possibilities to combine, you might say, analysis domains. So we have this domain about market analysis, where you actually would like to be better to represent some constraints in a good way. And that machine learning could be a way to combine this constraints. So you might identify constraints or look at the constraints in stability analysis, RMS, or even EMT. But then you can train a model on this, and then you can use it in your market modeling. So what you build is an operatable system. So you can, and we haven't done this. It's very sensible to say we would like to look more into this way of combined in your optimization, learning more about what's the parameters to deliver stability, because that's coming back to the key of what you asked in the previous questions. Actually, where do you place and how much grid forming do you need at what places in the grid, and could that be efficient delivered from some of these resources with battery in different points? So somehow you can merge this analysis domains closer together by using machine learning, but it's something we're looking into. So glad to hear the interest about this this issue as well. So yeah, and yeah, you have the slide here, and I think also there's a link in the slide to what the work done at DTU, and I know EPRI is doing good work on this area as well, and you at ESIG have been working on this, and we'll discuss it more. So yeah, thanks for the question on this.
Yeah, I think probably last question. We just have 2 minutes left, but I think this is kind of an interesting one to hear about. As the hydrogen system operator, as you said, are there any updates to the control room that would be more focused on the hydrogen aspect, different displays? How are you monitoring? How would you be monitoring the status across that system, and how does that compare to the existing monitoring systems for the transmission system?
Yeah, it's still to be worked much more with, because we're now in a stage where we have identified good economy in a hydrogen backbone. There's political agreement on going that way, and we got the obligation to find out what's needed in the control room to operate it, so we can simulate the situation. But it's a very good question. I think there's a lot to be done on this to understand how are we going to use or have a control room. Today we have our gas and electricity control rooms, but they are not, they're beside each other actually on the same side, but don't have so much in common. but the hydrogen, you have much more flexible dynamics. You have to co-optimize when you look at the operation. So you will need new way of looking at it, but we haven't done that much on this yet, but will.
Okay. Well, we're at the top of the hour, so I think we'll wrap things up. So I want to thank Anders again for his presentation today, especially for taking the time out of your late evening to present to us here. So I hope you get some good sleep soon. But as I mentioned earlier, we'll send an email out once the video file is posted, and if there are any other questions we didn't get to, we might have some responses there as well. So just thank our ESIG members again for their support. These free webinars are made possible through our ESIG members. Appreciate your engagement. Look forward to seeing you all soon. Just as a quick plug, the ESIG Market Design and Meteorology Workshop and the Large Load Task Force Workshop are coming up later this month, June 24th through the 27th in Nashville, Tennessee. So hope to see many of you there. Anders, thank you once again for this timely and informative webinar, and thank all of you for your interest. Look forward to seeing you all again in the near future.
Thank you, and thanks for the possibility, and thanks for all the good questions. So have a nice day and evening. And yeah, bye.
Thanks a lot. Bye-bye.